Yeah, I'm ready.
Hello everybody, this is Fabricademy 2019, week 8 Computational Couture with Aldo Sollazzo from Numena. I give the word to Aldo. He can introduce himself briefly and then he can start talking about what is parametric design and how we can make digital fashion.
Excellent. So thanks for the introduction. Ciao Anastasia. I'm not alone here. I'm also with Laura Civetti, and Laura is our expert in fashion tech, and she's also Fabricademy class 2017. So actually she was one of the first. She's from the first batch of graduated alumni from the Fabricademy. My name is Aldo Sollazzo, and I'm directing Numena, the Master in Robotics of Advanced Construction of IAC, the Global Summer School of IAC, and the postgraduate program of Design for Wearables in the Institute of European Design. So let me share the screen with you. Here we go. Do you see it?
Yes.
Super. Okay. So this is the third time that we are going through computation and fashion design. It's an interesting connection that is probably the one that is opening the most in terms of possibilities. New declination in terms of aesthetics and language that can connect a series of different inputs and parameters into the definition of novel aesthetics that can be generated from the digital side and affect as well the physical one through digital fabrication. So computational couture is a link between materials, characteristics, digital process of design, and is also the link to all the process of fabrication and making that happen afterwards. So consider the process of computational design as a transversal process that is parametrizing, translating in numbers, physical objects, physical parameters from the real world, and converting parameters into design tools that we can implement in our creative process of aesthetics and idea generation okay, this is a short video about I didn't even see it before, about a little bit of some exercises of the Fabricademy that we did in the recent years. But let's focus a little bit on what is computational design. Okay, so let's start talking about language. This is a connection that I always make, but if you search for the definition of the language, you will see that language is a series of instructions that are carried out in a specific order. So if you want to communicate to someone, of course, you are establishing, you are following a hidden rule, or let's say instructions that allow the others as well to interact with you, understand you, and receive your message. If you introduce the word automated in the description of language, you are not only describing language, you are also describing scripting. Okay, so you are also describing another process of communicating and developing, let's say developing forms, but not only forms, codes, since language is a code. And talking about code, there is an interesting relation that is described in this book that is very famous if you want to get a little bit more in deep with computational design. Is a book that Mario Karpov wrote. It's called The Alphabet and the Algorithm. And in this book, he's describing one of the first codes. So one of the first instructions that were written by a designer, an architect, and they were pointing towards the definition of a building. So Leon Battista Alberti, in the 14th century, he developed a series of instructions that are actually coordinates, polar coordinates, that the worker needs to follow in order to produce and generate its building. Okay, so let's say that this is probably the first moment in the history of design where forms are translated into a series of numbers and instruction for fabrication. So here you see exactly the relation that I told you before. the production of forms and the translation of these forms into a specific protocol for construction. And this is extremely interesting. If we jump a little bit to the 19th century, we can, in the 18th century, we can see that there were other the evolution that were made around the concept of computation. And in fact, Deleuze described in this book from the 18th century the niche of computational design. And computational design not only relies on this capacity of describing or translating instruction into a series of codes, so geometry and codes, but also the quality of variety. So the moment that we introduce parameters in the definition of forms and geometries, we are also defining a possibility of modification. And this capacity to produce variety, to modify parametrically by numbers the output of the aesthetic solution, is actually defining probably the beginning of computational design as we consider it nowadays. So you can even look at this drawing on the right side and maybe consider it as the first grasshopper script that was ever designed. And Laura is extremely proud of it. Okay, so jumping a little bit into the context of making, you will also see another special link that we are maybe exploring the most nowadays, in the last maybe 40, 50 years. And it's connected extremely, is even more powerful because it is connected strictly to the Industrial Revolution and the implementation of automation in the world of fabrication and making. But what it represents is also, again, the conversion of digital instruction into physical action of manufacturing. And you see that all these operations started in the car industry with the implementation of 6-axis robot, or at least this is, let's say, a first application where operations like that were starting to merge and combine bits and atoms. That is a hot topic in the Fabricademy and the Fab Lab world, and in the Fabricademy as well. Okay. Computational design, for what it represents, maybe integrates even a step more. So which are the parameters that are really affecting the design protocol? For sure, we are talking about parameters, as Anastasia said before, parametric design. One thing is parametric design, another thing is computational design. This is a small difference. Parametric design is the iteration of forms that are defined by a series of parameters, numbers that control their shape. Computational design is a process that is built on top of parametric design, but where the intelligence and the complexity of is established by a series of external forces that are integrating a higher sense of logic in the definition of a new aesthetic. In human sense means that we are starting to design with external input. They are not only directly affecting design itself, but are related to the design implication. For instance, environmental solution, structural analysis, etc., etc. All these material characteristics, all these parameters becomes design parameters, okay? Thanks to the data associativity, so the capacity to associate those inputs into a series of information that affect forms and geometries. But how can we inform these geometries, this aesthetic? So which are the protocols, the different criteria that we introduce in order to establish a workflow of computational design? So we have, this is just a series of slides that will somehow classify the main sectors of computational design. Okay, so we can define one of them as parametric modeling, as Anastasia was saying, so a niche sector of computational design where geometry and forms are strictly related to the association of parameters. So there is not an external intelligence that is controlling the evolution of these geometries, but as you can see, there is in any case a strict relation, I don't like the sound, strict relation between function and forms, and this relation is also controlled by parameters. This is a project from the winner of Reshape. We already saw it yesterday, if you guys were following the recitation, but it's interesting the way that all this Voronoi grid was implemented in the definition of these forms, and now as well different functionalities of these shoes were associated then to a specific protocol of fabrication. Right. So another, let's say, different approach that we can find in computational design is an approach that actually represents a different negotiation between the designer and the machine. So in this case, we enter in a protocol where it's not possible really to define the characteristics of the output, and we establish with the machine a co-creation process that relies on both, on the participation of both agencies, so the human one and the machinic one. So if you talk about loops and recursivity, this also is a definition. This presentation is shared with all of you, if I am not wrong. But you will see this is a very typical, I guess the video is not working here, we will fix it, but this is a typical process where the aesthetic output is actually the result of a repetition of a series of actions over time through a number of iterations that these actions are producing, and now these iterations are actually modifying and transforming forms and geometry. So here you can talk about fractals and then all the iterative design that is connected then to loops, cellular automata, health systems, etc., etc. It's completely a different world. Then also talking about emergent design, we have the huge sector of agent-based design. In this case, I mean, we are talking about the definition not only of actions, but actually the definition of behaviors. So what we are programming are actually agents that have their own intelligence, their own sensibility between their movement and the environment, and are starting to move freely in this space, but what the designer is producing is the set of rules that they need to follow for every movement. Okay, and this is a big field where, okay, we will need a little bit more of time to explore. Then there is a very interesting as well side that I love personally in the process of computational design, which is the implication of performance into the definition of forms. So computational fluid dynamics, all the sector of analysis and simulations as well, is what is as well affecting or directing the emergence of forms and geometries that are meant to be more efficient if compared to a very specific protocol, or let's say a very specific goal of analysis and simulation that they need to respond to. So computational fluid dynamics is a technique that is nothing new in the car industry, because remember that what we are implementing here is a series of tools and software and hardware that are developed from other industries, and that in these last years are starting to jump into the design protocol. Okay, I'm not screaming enough? No, I need to scream a little bit more. Okay, so grazie. So what I was mentioning here with computational fluid dynamics is what is happening in the car industry to simulate wind. Can you hear me, Teshi? I see you. Okay, all good.
Audio is perfect here.
Okay, super. I'm happy about it. So okay, I will show you later this project. Okay, I'm sharing the screen, but I don't want. Okay, I can move it around. So I will show you later what this is related to. We will jump into the specific process. But it's exactly what in the car industry you do with the wind tunnel. They are simulating the movement of air and understanding which is the best, most performative shape that can be the produce the faster car. And we will see how we can introduce something like this also in the making of new textiles application. Then talking about textiles, there is also the possibility to simulate textile behavior. And we in previous Fabricademy classes, we also been through these protocols that you might be a little bit more familiar with. Commercial softwares like Clo3D, for instance, are integrating simulation of clothes and fabrics into digital environments. But in this case, I mean, as well, it's very similar and it's connected to the integration of physical behavior into the digital environment. And this is as well what we are implementing, or we implemented, I will show you later, into the production of new aesthetic solution. We will jump into it and I will show you how. Then, since I'm directing the master in robotics and advanced construction, why not let's talk about structures. I don't know if you are aware, but many of you at the end of the year, last year, produced shoes. And a shoe, of course, I mean, is a super interesting structural system that could integrate a higher level of intelligence connected, if connected, also to tools that can simulate structural performance. And in Grasshopper, for instance, you have a series of plugins that can simulate structural behaviors as fin system or continuous shells, etc., etc. And all these simulations as well are translated in parameters that can affect your aesthetics, your solution, that can support even the effectiveness of your design protocols. And talking about aesthetics and structural behavior, there is another office. I don't know how many architects are there, but there is another office that is worldwide known. There is the Hadid, that presented many years ago a very famous protocol of fabrication together with Stratasys. And in this case, what it was optimized was the implementation of 3D printing materials into the definition of this chair, which is structurally optimized for the weight and structural performance. But the structural performance is controlling the amount of material that is deposited by the machine. And in this case, in fact, you can see the simulation of the chair itself, the smooth of this chair into a higher level of tessellation, and then what is run on top of this structural geometry is a mesh topology optimization. So according to the weight of this person, you consider weight loads, then support systems, and you start to understand how the material should be should disappear or should appear the most, should be integrated the most in some specific areas in order to be more structurally performative. But the interesting part is that all these instructions and protocols are associated from the digital realm to the definition of G-codes, so machining protocol for fabrication, okay? And this is also something that is not new at all. In the Master of Robotics and Advanced Construction, we also did a second iteration on top of this one, and I invite you also to have a look at the final result. Okay, but it's, I mean, at least still I think it's very valuable as a research. I mean, very valuable, we are talking about something of 2016. Okay, also in computational design, things are outdated very quickly. Then talking about what I said before, no? These different protocol or different negotiation between machine and designers. There is, of course, the big realm of machine learning, convolutional neural network, and then all the definition of new integration of machine decisions into the design realm. So Grasshopper in 2011, if I'm not wrong, introduced also new systems for evolutionary solvers. So this was really the beginning of protocols for machine learning that were based in the definition of goals and parameters, genomes that could support the implementation of the best, most performative solution according to a series of characteristics that the designer were setting up. So in this case is all the environment of the evolutionary solver, and it's interesting because what the designer is defining are the possible iterations of a series of parameters that can contribute to reach the most performative solution. What you see here, for instance, is the creation of random points into a a fitness landscape. This is how this form is described. And the only parameter that these, let's say the only goal that these points have is to find the highest position in space. So the variables that the system is using in order to reach the best solution is only the X and Y coordinates, but the fitness value is actually the Z coordinates. So what is happening is that all these evolutions are calculated by the machine until all points are sitting on top of the highest hill of this landscape field, fitness landscape field. Okay, so which are the sectors that we can tackle with computational design? Many. We are in the Fabricademy, so of course the one of fashion and making is one process. But and I mean, if we are talking about fashion design and computational design, for sure, nervous system has been leading a lot of with the early projects in 2012 or 2015. Some of the best, or let's say more interesting solutions, and as well these solutions were integrating the capacity of produce variety, and I will invite you to see here. So control geometry, forms, tessellations, and associate to this capacity to produce variety also the possibility to customize the shape, customize also the connection between body and geometries, and control in the same time all the fabrication protocol. So this is not something, this is a small exercise that we will also do in our class today, and it's an iterative tessellation that is controlled by just the definition of these different colors, and this iterative tessellation at the end is also controlling the definition of this new skin that they are producing, a skin that is of course 3D printed, and this is the final output. But of course, I mean, nothing is so simple. I mean, in order to fabricate then this piece, you need also to combine the different characteristics that even the machine has. So the interesting part in terms of computation that nervous system did here was to unfold the dress and understand how the dress could be folded in the minimal, occupying the minimal amount of space, and enter the machine. So as you can see here, the printing was rolled in order to be implemented inside, be placed, fit into the machine space, and then was fabricated. So an interesting connection between variety algorithms that are controlling aesthetics, definition of fabrication protocol, and also controlling this fabrication protocol according to the machine characteristics, which is great. Okay, and then jumping a little bit to this project. Whatever, let's go on. So of course computational design is implemented as well in interior design as another field, and here I mean we are introducing a lot of different aesthetics. Maybe here would be interesting to have we want to modify a little bit the presentation also some of the furniture that we introduce, or is also implementing different paradigm for artistic installations. For instance, here we have a code that has been implemented a lot also in computational design and in fashion design as well. You will see it. For instance, me and Cecilia have been working on a similar code for the definition of Coralia in 2017. That was a dress that was mimicking also a coral reef, and then associated to this computational code as well. Also, of course, instruction for 3D printing. This is a project between Zaadit and AI Build. The interesting part here is also the integration, as usual, of machining protocol and design iterations. So this is the shape. This shape is defined by a specific fabrication process that is called ruled geometries. So all these strips are actually planar systems that are then defined by a machine that is cutting, like here, I don't know if okay, you see, by a robot, a 6-axis robot that is cutting according to these planes. Is cutting a series of cubes and then is 3D printing on top of the final geometry. Okay, so even here you have a lot of creativity that is connecting even the multiple process of fabrication. Okay, that you can have multi-scalar process of fabrication that are all the time as well affecting the iteration of your aesthetics. This is a system that we implemented in the Global Summer School 2016. So I actually bought a lot of foam, and Ayak was exploding of foam, and we built a series of installation with the very same system. But the interesting part here is that on top of this foam, using 6 axes, the machine was also 3D printing. So as you can see, we are not only using 3D printing as a planar system that is mainly changing because of the height, but we are also using here all the 6 axis possibilities, all the rotation possibility that the machine is introducing. Okay, so I mean a very interesting protocol that is, I guess, is introducing a lot of complexity and possibilities for us as designers to interact. And then, of course, I mean, I'm jumping the one of construction, but all these words of computational design actually start here. So in 1992, in Barcelona, this architect that is called Frank Gehry got commissioned the construction of the fish for the Olympics of Barcelona in 1992. Okay, I hope nothing porno come out if I search for Gehry fish, Barcelona. Yeah, here we go. So this is the first implementation of computational design in construction. And it's interesting because it is the very first time that a series of geometry and forms are translated into machinic protocols of fabrication for architecture. So what do you see, or probably you don't see so much, but is a series of strips. So there is a discretization of all these different strips into custom geometries that are completely different one from the other. It was completely impossible to control such a complex shape is a double curvature system using normal softwares. So Frank Gehry, that is the same architect of the Bilbao, the Guggenheim in Bilbao, the Disney orchestra, the Disney opera in LA, etc., introduced a new software building on top of CATIA. CATIA was a software that was used by the car industry. It built on top of it this solution that was producing all the precise items that were completely different one from the other, to build in 3 months the very first output with computational design. And from there on, I mean, it's just history, no? So we started with Grasshopper, and then processing, Grasshopper, now the BIM, which is building information modeling, etc., etc. So all the stuff that you see here, of course, is tackling how computational design is implemented in different sectors. But let's see which are the protocols that we can control with computational design. I will be very fast here. I don't want to spend time to talk about 3D printing. So with computational design, of course, we can create custom G-codes. Okay, we don't have to rely on external software to create slicing solutions, to slice our geometries. We can produce all the items that are necessary for mold. Of course, we can control the system of laser cutting, the one of milling, etc., etc. Okay, now this is a new part that I added now together with Laura for this class, and I would like to show you a little bit how we send me a link to Vimeo with the Numena show you. Okay, I would like to show you a little bit how we use computational design in this office. So as I told you before, we are an office, a tech company that is implementing computational design in the definition of new aesthetics and language. So let me see, where is it? So the style link. Yeah. Okay, so I want to show you quickly this showreel that we did. Okay, well, I will not show you the video that we did for the presentation, but I will jump into the a little bit the description of some application that we did with computational design together with the Institute of European Design of Barcelona this year. If you consider why to work with forces and how we can translate the capacity of computation to convert into parameters external output, in this case we collaborated with an architect that is called Edouard Cabey in the definition of a mechanical geometry that can simulate how forces can manipulate textiles. So we built a machine, a crazy machine that was built around, let's say, a big frame that was built around a dress, and we connected, we created a grid that was connecting every single part of this dress to a specific point in this polar array coordinate system that was connecting every point to this machine. So you can see that the central part of this textile, of this dress was, of this machine was the dress itself, and all these points are the one that we were pulling with the strings. So we were applying an external force to the textile, and on the same side, on the same time, we were translating this deformation in the computational space. So this is a machine to physically test the implication of forces in the definition of aesthetics, and I want to show you a little bit which is the protocol behind to simulate how these systems works. Okay, look, this is a little video. So we are starting from a 2D pattern that is not complex at all. We are creating the relaxation of this mesh around the body, an invisible body, of course. And then we are digitally simulating the exact same phenomena of applying forces that Edouard was developing with his machine. But afterwards, we are associating to this deformation as well a protocol of fabrication. So we are discretizing or subdividing this geometry in a series of strips that then are sent to a laser cutting machine in order to be built and assembled. Okay, so this is, for instance, one protocol that is combining, and this is what I expect you to do in 1 week. I'm joking. No, I mean, this needs a little bit more. But I'm talking alone. But this is as well what we brought to all these strips that you see here, that then were strictly connected to the, bridge that we were making from the physical environment to the digital, and then back to the physical thanks to this protocol of fabrication. And those are some other output that we got. But also we started to integrate in this, in this protocol of fabrication, we also started to integrate manual craft and implementing threads. We started to explore how to combine back the strips. This was actually my favorite solution, but it was a bit hardcore. Maybe we could use pins, maybe, but I mean, it depends also on the fashion designer. Here, the guy wanted to use. Then we had also another collaboration also with the European Institute of Design for the Fashion Week of the Bridal. And here we collaborated with another department that is implementing solutions for wedding dresses. And in this case, we introduced a different material. So we started to work with ceramics, and now we could actually create a skin with materials that are not only of plastic, but are also natural material, and how we could even develop something, an aesthetic that is maybe more interesting because it's combining all these different materials and protocols one with the other. I don't like the output, but it was an interesting first stage where we were also combining external collaboration with, with another sense of craft that can be integrated in this new aesthetic. In this case, it's another collaboration we did last year for the Madrid Fashion Week. In this case, with a fashion designer that is called Ulisse Mereida, that we need to add to the credits here, and Marcelo Villar. So Ulisse Mereida decided to reframe the characteristics of the mannequins of Marcelo Villar, which is a company that is producing all these mannequins for retail spaces. And he created, let's say, he created an approach that is quite similar, I see very similar to the one of Mitorai. So this idea of also cutting bodies and geometries, creating some sort of decomposition. And the interesting part is that he started to decompose and cut the mannequins from Ulisse Mereida and started to recompose them back with the implication of these textile forms. And I found it, quite interesting. And we use, of course, computational design and 3D printing to reproduce and optimize even the fabrication of these pieces for the Fashion Week. And talking about the relation between material properties and computational design, if you saw the lecture of yesterday, you remember that I already spoke a little bit about VR Pure Tech. In this case, everything starts with the material properties, which as I said yesterday, for us is a crucial key, is a crucial point, the definition of a new paradigm for the fashion industry, and not only. Here, what we started to do was to integrate in the definition of new skin textile application this material that is absorbing carbon dioxide, nitrogen oxide, volatile organic compounds, and convert all these pollutants into environmentally friendly minerals. So everything starts with this powder that is developed by the office of PrimeLab, a Spanish company here. And we apply this powder to polymers. So we produce filaments and a pellets solution to scale up or apply this solution also to the world of 3D printed textiles. Together with Cecilia Raspanti and Back Society, Numena, PrimeLab, and Back applied to the world European contest, whatever is it, and we produced this first garment solution that we decided to call Wear Pure. So what it represents, in fact, is the declination of new textile solution into the production of a new application that is converting even is trying to decline the impact of textiles from a negative one to a positive one by allowing textiles application to be really agents or protagonists in the solution of global warming or climate change. And the protocol that we implemented here is strictly connected to the material properties and the computational approach. So what do you see is the decoding of all the characteristics of this body, the implementation of the specific curvature of this body into a new landscape that could integrate as well the definition of new parameters to allow the skin to be more performative for the CO2 absorption. So we implemented computational fluid dynamics to simulate the efficiency of the skin, and we played with the height of this wall in order to increase as well the absorption and the connection between air and CO2 absorption. So after this, of course, we work on the translation of this mineral into a polymer for 3D printing. We started to implement as well the machines of our partners at WASP in the definition of the new garment, and we produce some first outputs that together with Cecilia and PrimeLab, we've been presenting in the Dutch Design Week, in the Fashion Week in Milan, in Barcelona in Reshape, and in the Caixa Forum in January or in February, I don't remember. Okay, so this is a first output, and together with Laura, we are now defining new patterns that can also integrate novel aesthetics in the definition textile applications, and Laura is trying as well to mimic and optimize the characteristics of these forms and the protocol of fabrication using Grasshopper. You will see, because later she prepared a script that will guide you through this system, working not only with filament but also with pellet. Okay, so in terms of application, I mean, this is what I said before. So this is how we translated the curvature of the body into different landscape that were then decoding this information into spatial form using vector fields. So different forces that were producing all these different corridors that you can see on the bottom part. Then all these different geometries were optimized, connecting to the topic that I mentioned before, computational solvers, in order to optimize the absorption of CO2, blah, blah. This is what I said as well. I discussed about it. And you can see how from this landscape of geometries and curvature, we are jumping in the definition of all the different paths that the machine needs to follow to deposit filament on the textile. Okay, and of course we translated this path as well to respect the curvature of the body, understanding how then the material was bending according to the filament that was implemented on top of it. We fabricated, and those are some high quality images that we placed here. Okay, so this Grasshopper course, this course is based on Grasshopper. I can say by experience that at the end of this week you will ask why we are not using Blender, why we are not using Clo 3D, etc. And there is not a specific reason behind, but actually we like to work with Grasshopper because Grasshopper is not an open source tool. Blender is an open source tool, and if you want to work with Blender for computational design, you are more than welcome to do it. But the interesting part of Grasshopper is that it's a reliable ecosystem that has more than 10 years of existence. And the interesting part is that many different designers, developers, engineers have built on top of the existing infrastructure and developed a series of interesting plugins that convert Grasshopper into a powerful instrument for design. Okay, so I will guide you through the basics of Grasshopper. Actually, I will not do it because this is what Eugenio will do tomorrow. What I will probably do more today, I will show you how we can translate some quite famous garments into a protocol that respects the computational logic that I want to introduce to you today. Okay, so this is not a class of Grasshopper introduction. You can find online a series of classes that can guide you through it. Also looking at the previous courses of the Fabricademy, there are, if you can look at the other classes as well, you can find similar information. And aside from that, we have also have all our links and reference that are in our documentation. And plus, we are available on the Slack channel. You need to ask us something meaning references. Okay, so I guess there will be many different codes to fix, which is in human terms is impossible to do it with the time that we have at our disposal. But I will be more than happy to maybe channel your interest in some specific direction. So that said, let me stop sharing. No, I will not stop sharing. I will just start. So take 5 minutes or 2 minutes to open your Grasshopper script. Can you still hear me? Are you still there?
Yes.
Yes. Excitement, eh? Okay, so let me see here what we have. Let me see. Okay, as I said before, we will try to keep it more or less simple, so you are not scared about Grasshopper. Do you see the Rhino Grasshopper open on my screen?
Not yet.
What do you see?
Blue screen. Maybe
Okay,
you can just...
Okay, wait. I will share it now. Okay, can you see now my screen? What do you see? Ciao Angela.
Hi.
Hello.
Well, the rhino with the grasshopper besides.
You can see also Grasshopper, right?
Yes, we can.
I just draw a circle. You can see.
No.
No, okay, so you probably see the other one.
No circle, but we see the rest.
Ok, va bene, va bene. It's good that I don't do the introduction to Grasshopper, right?
Yes.
Okay.
What did you say?
That is good. I jumped the introduction to Grasshopper. I don't think it's. I mean, we can find it in many other places. No, maybe since we have few time.
Yes, we will do also this tomorrow, so you can
Okay.
into the subject.
Yes, let's go into the subject. So everyone, open Rhino and Grasshopper. If you have it open, give me a moment just to open my definition.
And now we have blue screen again.
No, you don't see my... Give me one moment only that I want to download one thing.
What you can do is that when you select share screen, you can just press on the upper part, which is saying just start sharing your screen without selecting which screen you want to share. The upper part, there is like a bigger...
Okay, I want to share the second screen. Whatever. Okay, now I'm sharing my screen. Can you see?
Exactly.
Super. Very good. Okay, so give me one moment only that I want my script. So last year we did a class that was quite advanced for Grasshopper. It was more connected to the simulation of clothes. Okay, this year I would like to start with something that it might be more useful for you, and it can also allow us to replicate some quite famous dresses that were developed by a colleague. Then we will see that is called Benaz Farai. We will see the logic behind the winner of the Reshape competition of this year, which is a very simple project in terms of computational design, but it's interesting how she translated the simplicity behind into an interesting process of fabrication. So let's start. Okay, so first of all, I would like to start, you see now my face, but I will...
Yes, we can see your screen.
Okay, great. I would like to start with this sample and introduce a little bit topic of vector fields. So, first of all, Benaz. Right. I think this is an example that I already showed you in the previous years, but it's something that is good to keep in mind. So I would like to replicate with you this kind of system, but I will like first to start with the basic logic behind. So we will design a little bit with forces, and we will discover how to implement vector fields in this specific environment. So first of all, very quick introduction to Grasshopper. Here, Grasshopper, first of all, is not complex. Don't be scared about it. It's quite straightforward how it works. The more you will use it, the more you will get familiar with this logic. Grasshopper is built on top of Rhino, is a plugin. Consider it a plugin of Rhino. And every designer, every developer that is creating a new library is placing this library in a software, in a platform that is called Food for Rhino, where you can download it most of the time for free and install it here. So the original, when you start to work with Grasshopper, you might have maybe 7 to 8 tabs. So here you have a series of tabs with basic components here that allow us to bring from Rhino geometry into the Grasshopper canvas. Then these tabs are called params, the first one. Then we have mathematical components that are, let's say, that are allowing us to operate all mathematical equation operations, etc., multiplication, divisions, manipulate domains, even introduce a little bit of coding, so mathematics. Then sets is actually associated to the structure, the logic inside the Grasshopper component. So we will see what happens inside. Every component, every box is called actually a component. This is a component. Every component represents a code, okay? And inside this code, the data, the information is structured in a very specific way. So in sets, we are manipulating the data structure. Don't be scared about it. This is also something quite easy. You will get familiar with it, maybe also with Eugenio. Tomorrow you can get into it, or your local instructors. Then in vector, from here on, is very simple. So imagine that all the complexity is in sets, I will say. Here, we need to understand which is the organization of information inside the Grasshopper component. Okay, that's it. Then what do we have are points. So we need to manipulate points, vectors, okay, just points. Then we have curves, points, curves, surfaces, surface, meshes. They are similar to surface, but actually they are built mathematically, they are built in a different way. Okay, so there are surfaces and there are meshes, but they are three-dimensional forms already, okay? And then we have something something I'm pretty sure that you are familiar with, which is operation of intersection between different shapes. So Boolean intersection, intersection between lines, etc. Then transformations as well, super simple. Scale, move, rotate, okay? All these operations, mirror, all these operations, if you are familiar with modeling software, are not new. This is something good. And then we have display. So we want just to modify or customize how we visualize things. Okay, that's a quick introduction to Grasshopper. Okay, so good. I would like to start with one exercise that is very simple. So, which is the end goal of this exercise? Is to create a first field of forces. Remember the example of Benazfarai. We will try to reach it in a moment with the script. So what I want to do is to achieve, let me first copy the script here. So I will show you first the result, and then we will copy one by one component after the other. We will replicate this process, okay? Now I don't know how much I need to run, but Anastasia will stop me with Cecilia if I am going over time. So, let's see here what happens. Okay, so let's say that this is what I want to show you guys. Okay, I want to create a pattern that will allow us to understand how to control these forms using vector fields. Okay, this is not complex. As you can see, this is the script, how it works. Okay, and we will now replicate this script one component after the other. So let's turn off all the script. Okay, and I will start in vectors, in params, geometry, and points. This is a component, and this component is orange because of one specific reason. Okay, so this component is orange because it doesn't have any information embedded. So I will right-click here, set one point, and I'll go back to the grasshopper canvas, to the Rhino canvas. Now you will see that this component is gray, which means that it is storing information. If I use a panel here, you will see that I can read the information that there is inside. So since it's a point, remember a point is defined by x, y, and z. Okay, so these are three values that are defining coordinates. Okay, good. Let's do it 3 times. So we will actually use 3 different forces that we can convert from the vector field. So we have one point here. I will place another point here, and another point here. Okay. So I'm doing that by just doing clicking on the component, right click, set one point, and then clicking on Rhino. Good. So I have 3 different coordinates, or 3 different points, and let's start to associate to these points forces. Okay. So I will go to vector fields, and I will use 2 kinds of forces: positive charge and negative charge. So how this works in vector fields, you can see that we have a first set of components. They are defining charges, so are defining forces: positive forces of attraction, repulsion, spinning forces, vector forces. Then we are creating a field that can combine all these forces together. Okay, and this is something that we will also integrate in a moment. Afterwards, after we create this field, we can visualize it, so we can see how these forces look like with a pattern, and we can also display, so map these forces in a specific plane. Okay, so to recap, these are the creation of forces. Here you convert all these forces into a field, visualize this field, and map these fields over a geometry. So this is my starting force. I decided before that I want to have, let's say, a negative charge. So let me go to set a number slider. This is called slider. I mean, introduction, grasshopper in 1 hour and a half is not super easy, but this is a slider, and a slider is creating one output. Okay, so grasshopper works thanks to input and output. You don't have to remember how, what it does every single component. Forget about it. Remember that you need to do one thing that is very rare in this society, which is read. So you need to read the input by just moving your mouse over the input. So here we are asking which are the points. Here is asking you for charges. Here is asking you for the decay. We will see what it means, and the boundary, that is an optional condition. We don't need it. Okay, and from the input, this code is giving you an output. Okay, so input and output for every grasshopper component. Okay, and they work like spaghetti, connecting these different cables from one output to the next input. So a charge can be positive or negative. It's not very visible here, but this point around it at the moment has these 4 arrows, because by default, that's why this component is gray, by default this charge is positive, is equal to 1. If we want to make it negative, then we double click on top of this slider, we set the slider as a floating value that goes from a domain that is equal to -1 to 0, I would say. And here we can control values that goes from -1 to 0. Okay, so this is the negative charge. The moment that the charge is negative, our point will have this kind of line arrows, because it means that this point is attracting all the other points around it. It's like a magnet. Okay, so it has a negative charge. If it's positive, it's like something like this. And in fact, this is the negative charge. Let's draw now the positive charge here. So I will go to vector, fields, point charge. Here we go. And I will connect my charge underneath. To copy this component, you just do it as you do in Illustrator. So you press Alt and then left click of your mouse, you connect here. In this case, I modify my domain, and I will say a domain that goes from 0 to 1. Okay, so here we go. I have a positive charge now here as well. And since I said it before, I will also like to use a spinning force here. Okay, to create another force of rotation of these of all the other points around this specific vector. Great. So in terms of rotation, let's say that I want to have a radius of 1.9, for instance. I can even type here directly my amount, 9.98, and I have now a domain, a slider that goes from 0 to 10. Let's put it from 0 to 2 in this case. So this is my radius. Oh, sorry, this is too small. Parametric design, and I increase its size. Here we go. Okay, and I also want to control the decay. We will see later what it is, this decay. So I have, just to recap, I have a force of attraction, a force of repulsion, and then I have a force of rotation, a spinning force. Okay, so this is a force that allows all our points to rotate around it. Okay, 3 different forces. I'm now erasing this thing here. Okay, now I'm merging all these fields together. So I will go to vector, field, and merge fields. And I will press shift. When I press shift and the output, you will see there is a plus here, which means that I can connect multiple outputs together. Okay, in this case, I'm creating a field. Okay, now all these forces are together, are combined together. That is perfect. But these forces are not affecting anything. Okay, there is not a single geometry that they are related to. So let's create a rectangle, as I did before, but I will do it again. I will go in Rhino, here, rectangle, corner to corner, and I will press shift because I want this rectangle actually to be square. Here we go, I will place it here. I will turn off the grid so it doesn't bother you for the visualization. Show grid off. Here we go. And I will go to Param, Geometry and Curves. Right click, set one curve. Here we go. This is my curve. And I will populate this curve by converting the curve itself into a surface. Okay. So I will go to Surface, Freeform, Boundary, Surface. Remember that a curves are here. I can import geometry from Rhino to Grasshopper from here. Param, geometries, I need a curve. So I call this curve, I place it here, right click, and yeah, and I have it in my Grasshopper canvas. Now, I want to create a series of points inside. So I will need to do in vector, there is in grid, this component that is called populate geometry. Okay, if I just connect my curve to the populate geometry, what happens? That is creating 100 points randomly on top of this geometry. But I don't have them inside. I want them to be inside of it. Okay, So for this reason, I am converting this rectangle into a boundary surface. So I will go to Surface, Freeform, Boundary Surface, that creates a planar surface from a collection of boundary edge curves. So I'm connecting this one here. You can see now I have a surface there. I'm connecting my surface to the geometry. And now I have 100 points inside of this surface. I can hide also the geometry in Rhino. I can even control the number of points. I can go to params, input, number slider, double click in the integer, and I can type 150, 160 or whatever. And you can see that, I mean, I can control the number of points that appear in here. Okay? Is that okay? I hope so. So I will turn off the preview. I can turn on the preview, right click here, or turn off the preview. So it's still active, but I'm just switching off the preview of it. And now I will go back to vector fields, and I will use the evaluate field and the field lines. I want to show you how these vector fields look like. So I will place it here, and I will say, what is asking for? I don't know how it works. So it's asking for a field to evaluate. This is my field. Then point, this is point to start from. So it wants to understand which are the points that are affected by this field. And I will say these are the points that are affected by these fields. And then I will see in a moment how to play with the steps. At the moment, it's also possible to see that there is a very strong impact with this spinning force. And this is why I can actually play with the decay. At the moment, the decay is 2. I can put this value from 0 to something. So I can lower it, and you will see that these, I will increase value so the decay is faster. So the effect of this force is lowering down faster than expected, you see. I can reduce it a lot, dramatically. And of course, the moment I reduce it, you can see that other forces start to emerge. So I will turn off this one. And you will see that at the moment I have a spinning force that is quite high in terms of decay. And let's play with the others. So let me see. If I can put a decay equal to 0.15, for instance, here. Wow, this is super strong now. Starts to reduce, etc. So same logic of before, but it's a parametric design, you see. It can be so thin that it just can affect what is close to it. And with this value, you can play, to control all the different output, also from the other forces. Okay. And this happens now. This code. Yeah, someone is going to interact.
Yes, please. The surface, I didn't get the component. That one.
Boundary surface.
Yeah.
I'm gonna activate the HoloLens. No, the HoloLens. The Holocaust. This component is called. It's called, what's the name of it? Bifocals. Yeah. And this component is drawing the name on top of every single component that we use with bifocals. So this is the boundary surface, populate geometry, and the field line. Okay.
Where I can find the boundary surface?
Boundary surface is in surface, freeform, boundary surface.
Okay, yes, thanks.
Roberto, is it you? I didn't see the video.
Yes, it's me.
Okay. I recognize the voice. Okay, cool. Ciao. All good there? Yeah, I hope so. I don't hear your audio, but I guess yes, you are good. So, okay, so this is a first example that I want to make to introduce to the logic that Benaz Farai is using in her dress. Okay, so let's have a look.
Sorry, Aldo, I have a question and about the forces that you produce. There are not lines, let's say, but it's just only that you can after translate as geometry. Let's say if you want to make some like manufacture it, let's say it is just only forces, no, but not really something.
No. These are lines. If you want, I can show you. These are lines. Look at here. Look, if you go to panel, and you place a panel here. A panel is always reading what is happening inside.
There are cubes, polyline cubes. Okay. Okay, thank you. That it was for me not clear. I was thinking that it's just only forces. But yeah, thank you.
No. These forces are lines, are producing also lines that you can use. But I mean, there are interesting visualization you can make also if you want to evaluate this field. There is one thing that they are producing. There are also the values of the vector, which is more advanced. But if you want to play with the evaluate field, this guy here is giving you a different output, which is the intensity of the vector. So here you have the field, and here you have also all the different points. And in this case, what you visualize are the values in terms of vectors that we can say that the forces that are pushing every point in space. Okay. If we have time for another script, I would like to show you how this is connected to another script that we shared in the past, which is in here. You can understand a little bit better this one looking at this code. Okay, so imagine that here we have points in space that are, every iteration are pushed away by a field of forces. Okay, so these forces are pushing, are moving an object thanks to a vector. Okay, when you move an object from one position to another, I'm moving now this object from here to here, I'm applying a vector translation. So a vector is like a coordinate that is defined by x, y, and z, but is also defined by a direction and intensity. Okay, so in this case, the direction is this one. This is the direction, and the intensity is the value of movement. Okay.
We are not looking what you are trying to explain, the intensity, and we are.
I don't know if you see my video, but do you see my video?
No, we are looking at just the Numena.
I will explain you later what is a vector, but
okay.
When I switch later to my video. I don't know what is the concept of later here. Let's see what we can teach you in this time that we have at our disposal. So let me do one thing. Let me comment the script so I can speed up a little bit, because in theory the class finishing at 6. So I will not go component by component. I will just show you what every script does. Okay, so give me a moment. Okay, so let's switch to the example of Benaz Farai. So the image that I showed you before, Benaz in this project is Carriers of the Gates. It's an interesting project that is working with shape memory polymers, computer vision, and if you don't know it, I mean you should know it, because it's one of the most famous projects in wearable technology, and I'm sure that you will get more familiar with it. But I will show you which is the logic behind. Okay, so let's consider an approach that is completely three-dimensional. We want to work on a portion of a body. Consider this is a patch that with Eugenio we cut over a shape, designing a form over the body. But if you look at this geometry, this patch is a mesh. So a mesh is defining by vertices, faces, colors, and normals. Okay, so in a mesh you have a lot of information. It's not only what do you see now with your eye, but actually is a lot of mathematical information that are embedded in this geometry and allow us to control and manipulate with a higher degree of complexity this shape. So what this code is doing is that it's taking this mesh, is exploding this mesh, extracting vertices, faces, colors that are not there, and normals. What is the normal of a mesh? A normal, you consider a plane, a normal is always a vector that is perpendicular, so 90 degrees to a plane. Okay, this is a normal. Is that clear, Adriana?
Yes.
Okay, cool. So we have this normal. So what I'm doing is that we are playing with this value. It's all numerical values. You will get to it. It's a more advanced. You will start little by little. I want to show you the capacity that this tool has to control forms and geometry. Because also Monse, that I guess is there, last year she was asking me for something more related to controlling the orientation of forms in the three-dimensional environment, if I'm not wrong, for the generation of a skin that she was working on. So we have these normals. These normals are starting from this vector, from this position, and are going in a specific direction. So if you want to visualize this direction, I will use a display vector display. So these are the anchors and those are all the vectors. So you can see that all these points have a normal that is going outside of the body. Okay, so what we are doing actually is just to twist, modify the inclination of these normals according to an external pattern, like a field, okay, that we are producing. So this normal, look at the drawing from Bennett's. Can you see a sense of rotation here? Can you see a rotation, a twist between the geometries? Can you see that this thing is twisting, right? Yes, no? Silence, okay. But is it yes, is it yes. So what we are doing is that we are calculating a degree of rotation according to a value that is going to be distributed all along this geometry, like a music that is distributed all along this geometry and is directed now, is associated to every single point of this mesh. Okay, so what we are doing is that we are calculating here the rotation. Look how easy is it? Just a couple of components, and from this orientation we are rotating this mesh. How? Because we are implementing a Perlin noise. Perlin noise is a code that was developed in the early beginning of computer graphics to simulate smoke. Okay, if you search for Perlin noise, if you search for Perlin noise here, is a technique, and this is another beautiful thing of computational design, etc. As I said before, a lot of techniques that are coming from different environments. So this is a Perlin noise. It's just the simulation of this effect of smoke that we're implementing in the early, at the end of the 80s in the cinema industries to simulate smoke with computer graphics. So consider we are implementing this pattern on top of this mesh here to calculate this rotation. So what we do is that we create a line between every point and then its projection in a specific direction, okay? And then this line is rotated according to the values of the Berlin noise, okay? And these values are also remapped. So we are remapping these values of 0 and 1 into a new ecosystem of degrees from 180, from minus 180 to plus 180, okay? So Berlin noise is the map. We have 100, let's start from the beginning. I have a mesh, I explode this mesh. I have, now I'm associating one value to every single element of my mesh, okay? One value. I don't know if I'm coloring the mesh here, but no. So I'm associating one value to every single vertex, according to this pattern of black and white, dark gray, light gray, etc. Okay? So I have many values for every point. Good, now I have my starting point, the vector, that is this vertical line that you saw before. What I want to do is that I will rotate this vector. Don't consider this movement here. It's just a tweak that we need, a trick that we use to exaggerate the aesthetic resolution. So what I do is that these values of Berlin noise are from -1 to 1, okay? -1 to 1 is not the domain that I want to use to rotate, to create this rotation. I want to have a rotation in degrees. Degrees, you know, is from 0 to 360 degrees, okay? So I'm rotating, I'm remapping this value thanks to this component here. I'm taking all the values from -1 to 1 from the Berlin noise, I'm remapping these values, and I'm creating this rotation here. Okay, I will share with you this script, so you will see how this effect of movement starts to happen over the skin. Okay, and then what I do is just a matter of visualizing. So I mean, let's say increasing the effect of these lines and coloring them in space. So let me turn this off. So this is a it's a more complex exercise, but you can see that with very few components, just applying the Berlin noise, you can implement this effect over this body. Okay. I guess I'm pretty sure this is more complex, but I'm available to discuss about it. But let's say there is yes, question. You have a question? No. Okay, good. So this is just a big leap, a big jump between the vector field to this one, but in terms of component, as you can see, not many. We are not using many components. Okay. And this is also something good to add. Now, I want to do a simple exercise, so you're not scared too much about what it is possible to do in Grasshopper. And I want to go back a little bit to the example of the reshape that we saw before. This shoe that was awarded in the last exhibition. You can like it or not. I mean, we don't pretend that always the best project win, but what it represents a lot of times it counts the most. So in this case, what is really interesting as well is this capacity to associate through one unique code different functionalities, different materialities to the shoe itself. And also, of course, a protocol of fabrication. It's not something complex, this system, and you will see it's way more easy to the one that I show you now with the Berlin noise. Much more easier. So Laura prepared a pattern to produce these shoes, this shoe, and I'm gonna copy this pattern here on my canvas. let me go on top view. So in this case, for instance, the easier thing that we can do is to work 2D. Okay, instead of working immediately 3D, we want to work 2D. So we want to start with a pattern that can be very similar to the one that you are familiar with in your fashioning. So what we are doing here, I will go a little bit step by step, because I guess this one could be easier to use but also interesting to do together. What I will do is that I will tessellate, I will create all these subdivision, this grid subdivision on top of it, and then we will use the data structure to control the different materials that we want to apply, and also maybe manipulate a little bit the aesthetic and subdivision of this cell. So, as I said to Roberto before, I will use again a boundary surface. So from a curve, I will go to surface, freeform, and I will transform this curve into a surface. As we did before, I will go to vector, grid, and populate geometry, and create all these different points inside the geometry. And then I want to do something very easy. I want to convert this geometry into a grid, into a grid that follows the Voronoi logic, which has been abused a lot at the early beginning of computational design. So we can already see that now every cell actually in space occupy a specific environment, a specific cluster, a specific portion of this pattern, on top of this pattern. What we want to implement is that actually these cells are all cut inside the geometry we want to use. So for this reason, I will integrate an intersection. So I will intersect this grid of cells with my initial curve, the one that is, with my initial surface. So I will go to shape, I will go to intersection, clearly, then shape and region intersection here, and will intersect my cells, Voronoi cells, with my initial surface. And let's see what we have. These things that you see here is the time of computation that this script needs in order to allow every component to work. Okay, so this component is taking 6 seconds to work, while this one 72 milliseconds. So be careful because it takes time. Sometimes for some components it takes time to send an output. Now we'll preview off everything that comes before, and we have our tessellated geometry that I'm pretty sure that Cecilia loves on top of the shoes. Okay, so now I will go to surface and let me see. Okay, now what I want to do is to control a little bit how they are organized in space. So, yeah. There is one thing that I want to do first. Yeah. So with this simple exercise that you will see here, I will talk a little bit about sets. So list and trees, just a little bit. Okay, but it will be maybe more clear after tomorrow's class that Eugenia will give you. But I hope will be also transmitted by the Fabra Barcelona. So now what we are doing is that now that I have regions, I'm calculating back my centroids. Okay, so we go to surface analysis, and we'll calculate from these curves my centroids. All these points, like the one that we had before, very similar actually to them. Now, what I want to do is that if you look at the project that that was presented for Reshape, the name of the designer, Adara. We need to add the names of the designers here. Okay, so what is happening here is that Adara is treating in a different way portion of the shoe. Okay, So let's do one thing. I will say that maybe I will draw a central line here. And I will say that according to the distance from this central line, we might apply different materials. Okay? That is more or less what I can see here. More or less, something similar. So we can see that there is a material here at a certain distance, another material here, and also another material underneath. That, of course, is not part of the one that Laura unrolled in here. It's part of another surface. Okay, so what we have is this geometry. I'm now calculating the distance, so I'm also implementing, let's say, another mathematical action that will support the way that I extrapolate this form. So I will go to vector, point, and closest geometry, full geometry, here, full point. So the geometry that I'm using is here. So I will go to params, geometry, and curves. I will import this curve into Rhino. So now this curve is in my grasshopper. I will say that those are my centroids and this is my geometry. So what is happening is now I'm projecting all these points on top of this curve. Okay, and I'm calculating the distance. That is perfect. So if you want to visualize it because you are unclear, you have unclear what happened, I'm gonna go to set primitive and line and say that this is my starting point and this is my goal. So this is the movement that I'm making. From here projected to there, you see? So this is the projection of all these points on top of one geometry. As an output, I'm getting the points of projection, are this one, and then the distances. I will play with the distances, okay? So I will try now to sort all these cells according to the distance from this initial curve. So I will go to set list in list, and I will sort my list. What is a list? A list, something that we can see here in panel params, input, and panel. A list is this list of values, and we have 100 values from 0 to 99. So for every projection, we have an actual distance. Now, what I will do is that I will sort, so I will reorganize my list according to the smaller distance to the higher distance. Okay, so from something that is random at the moment, so from 26, one point was at 26 centimeters, I don't know, millimeters. Another one at 42 millimeters, etc., etc. Now we will organize this list from the shortest distance to the larger distance. So from 4 millimeters to 61. Nice. And aside from organizing these components, I'm also organizing another thing, which is my cells. So these are my keys, and I'm organizing my cells. So now the first cell will be the one that is closer, and the last cell on my list will be the one that is farther away. Okay? And if you want to select them, you can go to set list and list item. And the list item is a component that is helping you select one item from your list. So the closer one, as you can see, is this one. This one is the one, in fact, that is touching my curve. And this changes, you see, if I place my curve in another position, here we go, we can see that the closer one, the closer cell becomes another. Nice. Okay, so let's go on. What I want to do is that now I want to split this list into a bunch of different structures. Consider that the list now is only one list. It's like a tree. No? So at the moment we have a tree only with one trunk. Okay, so this is a tree with only one trunk. It's only one list. Okay? But I can split this list from one trunk, create multiple trunks, multiple branches. Okay, everyone with his leaves. Okay, so let's see. At the moment, I have only one tree. This is data structure that you are making. So this is one tree. Only one tree. And what I want to, sorry, only one tree. What I want to do is that I want to select, I want to create multiple trees. I want to cut, or let's say split this list into multiple directions according to the distances. So every distance actually is creating a domain of values. So I will go to math domain. I want you to think computationally, so in mathematical terms. I will go to math domain, and when I will extract the domain boundaries, and I will understand which is the smaller value of my domain, which is 2, and the higher value of my domain, which is 58. I will extract these two parameters individually. So I will deconstruct my domain. Remember that this component tells me that this domain goes from 2 to 58, something like that. I will deconstruct this domain, and I will pick the first one, the biggest one, and say, okay, if this is the value of my domain, okay, this is the value of my domain, let's split this value 3 times. I want to create 3 groups. So I will create actually a division. I will go to math, domain, and division. Divide 3 times this value, and we have 19. Okay. So let's see now what I will have to do. I will go to set, list, and partition list. So I will now cut this list according to every 20 items here. I will use as a starting list on my partition list the initial cells here. And what we have here is a collection of different chunks. Okay, so remember we had 100 items, and now I have 2, 4, 6, 8, 10, I have 5 different chunks, so 5 different portions of the initial list, so 5 different branches that I can treat differently. And if you want to visualize it, you can go to params params utility and param viewer, and you can see the structure of this tree. Okay, so the same information that before was stored inside one unique list, this guy here, is now stored into a tree structure. Okay, so we have 5 branches with 20 items each, when before we had 100. But let's see why I need all this stuff. Because I want to have more control in the way that I manipulate forms. To integrate a data approach to the manipulation of the geometry and the application of different materials. So, for instance, I have 5 different organizations. I can extract this number of 5 from the tree structure. So I will go to set, tree, and tree statistics. That will tell me that I have 5. Tree statistics is telling you the tree organization of the data of this data set, and it's telling us that we have this kind of paths. These are the names of our paths. The first one, the first branch, the second branch, the third, fourth, etc. And we have 5 branches in total. Good. So now I will color them differently. We'll go to params, utility, and I will, params input, and I will use a color wheel. So I'm creating 5 different colors, and I want to color these different chunks according to this guide. So I will go to display, preview. These are my chunks, and these are the colors that I want to work with. I graphed and simplified, but this is something we need to see in another moment. Sorry, I will create first the boundary surface. And here we go. So in this case, imagine we are defining the materials that we want to apply. So maybe the first one is leather, the second one can be 3D printed, the fourth one we want to work with the fourth one and increase the subdivision of this specific part. And if you want to work only, for instance, with the last one, look at it. Let's go back to set 3 and 3 branches. These are my trees. Okay, and I will pick the last one. So in coding, when you want to pick the last one, you can type -1. And -1 gives you an error in this case. So we're going to type 4. And we have the 4 value here. Okay, so imagine if you want only to subdivide this one, look, and now I'm working only with this guy. You see, if I want to apply another material, I type 3 and I'm working with this other guy. Okay, if you want to subdivide this thing in a different way, you can divide by 4, for instance. You can divide by 2. Like 2, we have 3 chunks. By 1, like 2, like now I have only 2 different materials. Okay, so for instance, if I want to work only with the last one, here we go, I'm selecting it. And let's consider that I want to populate it again. I can go to vector, grid, populate geometry. Remember that this has to be converted into boundary surface. Okay, and here, for instance, we are integrating more points, okay, that we want to cut. So let me only show you this part. And we'll turn off all the previous script. You see, now we are working only on this part, only on this portion. Maybe I also want to change the seed value, which is the algorithm, the random algorithm that controls the position of these points inside my geometry. Yeah, something like that. It's funny. And I mean, I can just repeat, for instance, what I did before. So I can, I don't know, I can create another tessellation, Voronoi, no? Like I was doing before. And I can say that this Voronoi tessellation, for instance, it can be cut by intersection, like I did in the previous example. So these are my initial curves. Sorry, these are my initial the curves that I want to cut, and this is the geometry that I'm cutting. And here we go. You see? And in this way, I'm just repeating the operation that I did before, but I'm increasing, you know, the subdivision that I can perform over this stuff here. No? Is that clear?
Yeah.
I know that. See, no? I mean, I don't think it's very complex. But you need a little bit more of practice to understand also why to work with data. And you can directly see the connection. All this stuff that I'm pretty sure was Chinese to you, sounded like Chinese, is the third class of grasshopper. So maybe after a couple of hours, you grasp all these data structure. And only by using numbers and mathematics, you can control, you can increase the control that you have with forms, and look at the strict connection that has also with design. Okay, I mean, like it or not, but try to understand the implication that he has, okay, with design applications. Okay, good. So Nastasia, How are we in terms of time?
Way over time.
Over. Okay, but I just want like to. I mean, even if we are done, I will take only 5 minutes more to show you what Laura
You can
prepared.
continue because people they can see from the recording afterwards, so no problem.
Okay.
You can continue.
Okay, I will just take maybe a little bit more time to show you a pattern that Laura prepared. I'll stop 1 second the sharing because I would like to show you the physical prototype. Laura, can you bring me the physical prototype? Laura, mi porti il prototipo fisico per piacere? All is good. We were completely ready for it. Cecilia is smiling. But you will see, I mean, this is something that Laura, before or after, I don't remember, after maybe Fabricademy, she worked for a little period for Iris Van Arpen after the Fabricademy. And they were preparing this exhibition, was Between the Lines, and they worked a lot with these thin patterns that had a lot of flexibility, and this is a pattern that Laura wanted to mimic. And Laura, can maybe you want to say a word? Let's say something about the material.
Hola, hi you guys. So this pattern is quite interesting from my side because it's not working with the material but works with the geometry. So basically, just according to the geometry, you can apply a stretchability on a material that is not stretched. In this case, we use a flex material, so yes, it's stretchable, but even if you apply on a stiff material, it could be applied in the textile with the laser. You can add this property to the material, and in this case, we laser cut. And we 3D printed, I'm sorry, we 3D printed, and even if we was using a PLA, I guess, we was achieving the same results. Probably not with the same amount of stretchability, but quite well. So in 40 centimeter of 3D print, you can achieve, I guess, 1 meter at the end. It's quite interesting. And from the script that we made, you can play with different level of the point to change this stretch.
Mi porti poi altri pattern se li puoi prendere un attimo?
Yeah, sure.
Okay. In any case, this is what Laura then developed in Grasshopper, and I'm gonna share again the screen. 1 second, I want to go back to our. And then I will close the lecture. So
And maybe it's also good to show the applications of this, like the Iris Van Herpen patterns.
Yeah, okay,
Of this,
sure.
3D printed, where it comes from. Yeah.
Yes.
I mean, she laser cuts instead, but.
See, exactly. I mean, she laser cut it, but Between the Lines, if I'm not wrong, was
something like that.
Iris Van Herpen. Yeah, Between the Lines. I have a strong memory, as you can see. And okay, I mean, there are some.
No, not this one.
Maybe, no, this is something that we did in the Fabricademy.
No. Above, up.
No, it's not this one.
Up, one up.
No, it's also, no, this is similar to this.
No, one up.
This one? No.
Left.
This one.
Yeah.
Yes. Yeah, you're right. Good.
I recognize them everywhere.
Yeah. It's this one. I mean, this one is exactly what Laura has been working on. This is my Facebook. I don't know if we can zoom a little bit on it. But I mean, in any case, you saw. Here we go. We can see a little bit better.
No, just because it's beautiful the way it moves.
See, I mean, it's super elegant, as you can see. I really like it. This pattern is super elegant. But I want to stop 1 second sharing again the screen. These are other things that Laura is studying. And for instance, this is another pattern that is interesting because it has stretchability only on one direction. In fact, I mean, you cannot really stretch it here, it's impossible, but it has a lot of stretchability here. Isn't it simple, but I mean, it's interesting because we are integrating then the CO2 absorption to these patterns. And as well, they are starting always with the...
It's super cute, this one.
Yeah, she I mean, hello. She did a very good work with this research. And I mean, those are all small iterations that we are making, testing also the capacity of our CO2, the We Are Pure Tech material for the textiles application. So it doesn't really, it has also the physical, the mechanical characteristics of textiles. Okay, but I want to show you an approach that is not mine, is the one of so quickly how she developed the code of Iris van Herpen. Oh, I mean, it's also a code that it wasn't invented by Iris van Herpen. It's just that you cannot hear me. Yeah, you're leaving. You can hear me. Okay. Okay, so quickly saying, okay, she's starting with 1 point, then she's moving this point down. So she's creating, okay, she's creating a line. Then she's creating a line, 2 points. Subdividing the first point, okay, you don't see my face, you don't see me. So she's creating 2 points, subdividing, moving this point in one direction here. So she's creating a curve. Then she's moving this curve underneath. And what she's doing after is that she's mirroring this curve, something like that. Okay, is an approach that she used. And then what she's doing is that she's creating an offset between this curve, okay, and shifting a little bit the result of this offset. So just to repeat.
Also, I think we are not looking what you are doing. I think that I don't know, something.
Can you see my drawings here? Ah, no. Sorry. So yeah, I'll share the screen again. Here you go. So just to repeat what I said, I mean, she's starting with 1 point. She's moving this point up. It's is less mathematically based, but is good as an approach that of a designer who want to model something, a pattern with grasshopper, closer to modeling than computational design. But she's creating 1 point, moving it vertically, subdividing this line, moving this point here in Y direction. Then she's drawing a curve between these points. Copy this curve underneath, then mirror this curve like this. Okay? Okay? And then what she's doing is that she's creating an offset of this stuff. Okay? And what she does after is just that she moves this offset down. So she has something like this that I'm drawing on the software, which is not easy. Okay. Is that clear? Let's see it in the code. So we have our point. As I said before, we create a series of points. We move some of them in one direction. Okay, like the line that I said before that I want to draw. Then she's moving everything under, she's creating other control points. Yeah, so she's basically just creating the points that are needed in order to create this curve in a series of actions. She's repeating. Sorting all these points according to the height, so the value in Z. Sorting these points according to the value in Y, creating a curve. Okay, so she's creating a curve. You can even do it by hand. This part, you can even do it by hand. You can draw it like this. You don't have to follow this logic. She is using it because she wants to increase the control. You can even do it by hand in Rhino, but I mean she's doing it in Grasshopper because maybe she wants to, I don't know, she wants to control, you see the length of it. No, it's parametric. That's why she's working like that. Okay, now I modify the parameter. Let's see if this works or not. Adriana, don't laugh because I see you laughing there. Then she's subdividing this line, creating all this curve, and she's moving this curve on top. As I said before, whatever, she's moving this curve and shifting them. Now I modify, okay, you see, I modify the parameters of before, so maybe I lost the final pattern that she wanted to make. And she's not here. Okay, but in any case, she's creating this kind of pattern that is not, that can be 3D printed, kind of continuous. And it's, all these gaps that she's leaving actually are made on purpose, because she also knows that the thickness of the material that is printed is always allowing the two lines to interconnect, to be locked one with the other. But she has quite a lot of capacity to, you see, to control how these things can be distributed in space. So it's just a couple of parameters that allow her to even play with the flexibility of the material, no? Because it depends also on the way that intersect with the initial geometry. Okay, so at the end, this is more, I guess, an example of parametric design, no? How these things interlock, how they are distributed, which is the degree of, you see, of rotation that they have. Okay, it's not so complex, it's quite basic, but it's interesting and smart the way that she uses it to play with this line. Look, let's have a look again from what you saw to the small pattern. You see, there is always the same line that it just moved. There are many approaches. I mean, this is the one that she made for the moment. Adriana is trying to explain how the flexibility process works. But okay, that is one output of it. Okay, so usually I have a course of 60, 70 hours of Grasshopper when I go over all the range of possibilities that it has. But I mean, you don't need it to start producing first iterations. I suggest try to start with a bidimensional pattern. Okay, you will see in the class of tomorrow that is more basic. It goes step by step with some clear example, easier example, how you can start to control this kind of shapes. So from grids that are very regular to variations. Okay, this variation is also controlling, again, the stiffness, the local stiffness of material on this side. Okay, so it becomes interesting when you want also to apply it to, you know, for instance, specific curvatures of the body. Okay, which is something that is interesting as well to implement and play with. Okay, so that said, I will close here the class of Grasshopper. Introduction to, I mean, it's not an introduction, the Computational Couture lecture from my side. And good luck with the class from with Eugenio tomorrow.
Yes, so we will have some classes with Eugenio tomorrow, Thursday and Monday. And we will connect and record them for everybody so that we will connect in the same address. And so tomorrow, if you want to connect with us, we will have a Grasshopper tutorial from 12:30 to 5. And then on Thursday, we have from 3 to 6:30. Yeah. And then on Monday, we have from 12:30 to 3:30. So we will be connecting in the same address.